So let's take a look at a couple of examples, get right into it. The first one reads 3 squared, or to the second power, times 3 cubed, or to the third power. So what we're doing is 3 times 3, which is 3 squared, times 3 times 3 times 3. Well, those are all 3's, aren't they? And if you remember the associative property that we talked about earlier that works for multiplication, that says that we can regroup all of these. How many 3's do we have all together? Well, we have 5 of them. So this is going to be the same thing as 3 to the 5th power. And 3 to the 5th power, if we were to multiply it out, 3 times 3 is 9, times 3 is 27, times another 9 is 243. And that is 3 squared times 3 cubed. All right, let's take a look at this one here. It's a fraction this time. We're doing 5 to the 6th divided by 5 to the 2nd, or 5 to the 6th over 5 to the 2nd. So on top of the fraction, we have how many 5's? Yeah, 6 of them. 1, 2, 3, 4, 5, 6 being multiplied out. And then on the bottom, we have a pair of 5's being multiplied out. Well, now wait a second. Since this is a fraction, and we've already got basically what would be the prime factorization of what this fraction's eventually going to be. And remember, you always want to reduce your answers. Can't we do something here? Yeah, this 5 would eliminate that 5. And this 5 would eliminate that 5. So what do we really have here? What we really have is simply 5 to the 4th power. That's 5 times 5 times 5 times 5. And 5 squared, or 5 times 5, is 25. 25 times 25 is 625. And like I mentioned earlier, these two numbers, 243 and 625, it would be very, very useful to commit that to memory as much as possible. I know that we're just going to keep adding and adding numbers that you'll want to, just kind of keep in your head. But it really does make things easy if you can memorize all of the powers of 2, actually all the way up to the 10th power. The powers of 3, really just up to the 6th power will do you just fine. And then beyond there, remembering 5 to the 3rd and 4th power is very useful to you. And remembering the cubes of, well, most of your numbers, all the way up to 9 or 10. All right. And so let's move on now, because we've got some negative exponents being worked through here. We've got 1 over 5 to the negative 2nd power. And I've already printed on here that that is changed to 5 to the 2nd power, which is simply 25. Keep in mind what we've learned before, that a negative exponent, all you need to do is basically flip it. All right, and then we have 1/2 to the negative 5th power, which I already printed it on here for us. When flipped, becomes 2 to the 5th power, and 2 to the 5th power is 32. So let's take a look at 2 of the things that happened earlier. If we look back, did you notice what we did here when we changed this into this, or we changed this into this? I want to really explore that a little bit. So right here is the first example. X to the m power times x to the n power equals x to the m plus n power. The base is the same in all these cases. Like in my example for this here is 7. And the exponents in this case are 8 and 3. And 8 plus 3 is 11. So what we really have here is 7 to the 11th power. And I'm not going to ask you to work out what 7 to the 11th power is. We don't need to worry about that right now. The point is we are starting to look at some of the properties that we can use to simplify some of our statements. And then much like our second example on the last slide, x to the m power divided by or over x to the n power is x to the m minus n power. In this case here, we have the base being 5, and the exponent is going to be 12 minus 5, which is 7. So what we have here really is 5 to the 7th power. And again, I'm not going to say, hey, let's find out what that number really is. The point is 5 to the 12th over 5 to the 5th is the same as 5 to the 7th. Less work to do. And let's take a look at some of the other properties that are true for exponent. Let's build another one. I have here 3 squared also being raised to the 3rd power. So according to the rule of order of operations, we would do 3 squared first, which is 9. And then we do 9 cubed, which is 27 times another 9, which is 243. Oh, 3, excuse me. But I want to simplify that. Whenever you're simplifying exponential expressions, what that really means is try and get it so you really only have to do one thing. Or if you were to do it with a calculator, that you're only typing one thing in here. We had to do 3 squared and then we had to do 9 cubed. I don't want to have to do all that work. So let's come up with a rule for this. 3 squared is 3 times 3. And that number, whatever that is being cubed. So that means we have 3 of those. And remember, associative property still works for straight multiplication, and they're all 3s. So how many 3s do we have written down right now? There's 6 of them. So 3 squared, then raised to the 3rd power, is the same as 3 to the 6th, which hopefully you recognized when you saw me write the number 243 down. So what's our rule? The rule is any base x raised to the m power and then raised to the n power is x to the m times n power. You might hear this referred to as the power to a power rule for exponents. Let's spend a little bit of time on this page. This is where I'm going to kind of condense all these properties that we're talking about onto a single slide. We did just deal with this one 2 slides ago. If you're multiplying the same base together, you can add the exponents. Here, if we are dividing the same bases, we would subtract the exponents. And then here is the one that we just learned, the power to a power rule. If you raise any x to the m power and then again to the n power, you can simply multiply those exponents together. Now, I've added 2 more here that we haven't talked about quite yet, but I hope you recognize what's really happening here. We have x times y to the m power, and I split that up to x to the m times y to the m. Or with division, I have x over y to the m power. It became x to the m over y to the m. What property that you've already learned, not even part of this lesson, but from earlier, is this really mimicking? Does it look a lot like? The distributive property. And this is a version of the distributive property, really. If you remember the order of operations, and let's leave the parentheses part out of it, but what's the first thing after parentheses? Is exponents. And then the next ones are multiplication and division. And I like to put those on the same level because one of them doesn't really trump the other one. You generally just go left to right. And then the last two are addition and subtraction. Now you already know that multiplication and division distribute over addition and subtraction. It went down one step along the order of operations. And what we're doing here is the same thing. We're saying that exponents distribute one step below them over multiplication and division. And I'm giving you this visual to point out something very, very, very important. And that is, does this happen? No. That's why I did it in red. Exponents do not distribute over addition and subtraction. That would be skipping a step, and the distributive property does not allow you to skip a level in the order of operations. You can only go down one level. Exponents will distribute over multiplication and division, and multiplication and division distribute over addition and subtraction. And that's going to be really important as we work through a couple of the examples on our next few slides. So, let's take a look at what we've got here. We're going to work out this problem and see what the answer is going to be. Parentheses comes first. Now, based on what we were just saying moments ago, can I do any kind of distributive property here? No, I cannot, because this is an exponent and this is subtraction, and that would be skipping a level of our order of operations. So we'll just do inside the parentheses, 6 minus 2 is 4 to the third times, make that look more like a multiplication dot, times 4 to the negative second power, which I can either leave it alone or turn it over 4 to the second power. We can go either way on that one, and I'll work it out both ways for you. And then we have 6 plus 2 to the 0 power. That would be the same thing as 8 to the 0 power. But you already know something, don't you? We didn't even have to do this, because what is anything raised to the 0 power? 1. So when we had 6 plus 2, whatever that is, doesn't matter. Answer is going to be 1. So, what do we have now? We have 4 to the third times 4 to the second, which, if we combine those together, we can do it that way. If I had left it alone, we would have had 4 to the third times 4 to the negative second, which would have been 4 to the 3 minus 2, which is what we're about to do right here. So, like I said, it is going to be the same thing. But 3 minus 2, either way, you're looking at 4 to the first plus 1. 4 to the first power is simply 4 plus 1 is 5. And that's our answer. All this stuff here simplifies to simply 5. How'd you do? Good. Let's take a look at another one here. It already has a fraction built into it, but let's see what happens. On the far left, we have 3 squared and then raised to the 6th power. According to our power to a power rule, that's going to become 3 to the 6th, 3 squared and then raised to the 3rd power, times, inside these large parentheses, let's start with 7 minus 4. That's going to be 3 squared over 3 to the 6th plus, and we have 9 minus 3 squared. 9 minus 3 is 6. So it's really 6 squared. Okay, let's keep going. We have a fraction here. The bases are the same, so we would simply subtract the exponents. What is 2 minus 6? Negative 4. So this becomes 3 to the negative 4 power. And I'm going to avoid doing any real arithmetic as long as I possibly can, so we'll just leave that alone. And now we have the same base being multiplied by each other. So we can go ahead and add the exponents. What is 6 plus negative 4? Well, we're doing 6 plus a negative, so we're really subtracting. That's going to become 3 to the 2nd power plus 6 to the 2nd power, which at this point it's really easy. Remember, I told you earlier in another video you really want to memorize as many of your squared numbers as possible. But 3 squared is 9, and 6 squared is 36. And we're just adding those two numbers together, which equals 45. So all this stuff here, as complicated as it looked, just equals 45. So let's just do one more. And this time, let's talk about it. We want to compare the values of x to the 7th times x to the negative 3rd and x to the 7th over x to the positive 3rd. Well, how do the two values compare? They are the same. That's right, they're the same. Why are they the same? Well, let's take a look. Using the one on the left, we're going to do x raised to the 7 plus negative 3 power. And the one on the right, we're just going to do x to the 7 minus 3 power. So we have the same two numbers. In one case, we are adding with a negative number involved. And here we're going to simply subtract, which is the same thing. Either way, both of them are going to be x to the 4th. And we know that by applying our properties of integer exponents. And that concludes our second video on integer exponents.